Hi everyone, so this will be the first video in a series of videos where I'll be introducing the short problem topics in ACSL. And as you can see here, today we're covering computer number systems. So let's get started with a quick intro to what it is before we learn how to solve its problems. So let's first define what number systems are. Number systems are the way that we represent numbers. And the most common one we use is the decimal number system, which is in base 10. You can indicate what a number system is by, let me show this. For example, if you had the number 100, we can indicate that it's in decimal form by writing a subscript 10. Okay, so how do we use number systems? Why do we use them? They're generally used by electronic devices to detect if a signal is on. This is the case for binary systems. The most commonly used computer number system is in base 2, which is binary, octal, which is base 8, hexadecimal, or hex, which is base 16. I'm sure most of you have heard of what binary is, given that most movies depict hackers with ones and zeros flying across the screen, and some of you may also know that these are called binary digits, short for bit. And the common way to use hexadecimal numbers are to represent colors. For example, you can see here that this indicates the color red, green, and blue respectively. They have different ways of representing this in different languages. This is mostly used in HTML. In Python, there's a different way of writing this. And as you can see, it's a number that comes in 6 digits. The first two are indicating how much red there is in this color. The second two are how much green there is. And the third is how much blue there is. And we'll learn what F means later. Alright, so the first thing we're going to learn is how to convert these different number systems into decimal form, which is our most commonly used form. First of all, we need to know what these things really are. Binary is a number system where you can only count up to 2. In the same way that in decimal we can only count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, except when we reach 10 it becomes 2 digits. In binary, 2 is our max. In other words, when we reach 2, we just kind of delete everything in between and we go directly to what looks like a 10. In octal, we have a slightly bigger variety of options. So we can go from 0, 1, 2, 3, 4, 5, 6 to 7. And then once we reach 8, that's our new 10. In hexadecimal, the idea is the same, except this time it's going to go a little bit past 10, all the way up to 16. 14, 15, 16. Except once we reach 16, once again, this becomes our new 10. Then you might say, well, how do we know if this 10 is the same thing as this 10? Well, in hexadecimal, we write everything that basically goes beyond 2 digits, but still counts as 1 digit in hexadecimal. We rewrite that with an alphabetical character. So 10 would become A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, 15 becomes F. And you notice here F is, again, we saw that on the previous slide, that indicated the color. F being the largest hexadecimal digit. So therefore, now we have a counting system that goes from 0 to 9, and then starting from A to F. And finally, 10 is, counterintuitively enough, 10 is after our other 10 here, A. Okay, anyways, to convert these to decimal, we have to For example, in binary, take the sum of all the bits, nth bits, multiplied by 2 to the power of n. Let's see an example of this. Okay, let's say we have the number 101. What does the nth bit mean? We're gonna count this like we would in array indexes in programming. Except this is going from right to left. We're gonna start from 0 and then 1 and 2. The reason we're gonna zero index this count is because the way we're adding up this number, or rather evaluating it into decimal, is that we're gonna take each digit. So starting from the right with 1, this will correspond to this entry here actually. We're going to multiply it by 2 to the power of 0. And you notice this 0 is going to be the same thing as our index here. And then again, we're going to take the next entry, this 0 here. It's at the 1 index. We're going to multiply that by 2 to the power of 1. And so on. Well, I say so on, but we only have one more digit. And that we will multiply by 2 to the power of 2, which is this entry right here. And then we can solve for it like we would in decimal. This becomes 1 times 4, this becomes 0 times 2, this becomes 1 times 1. And when we add all that up, we get 5 in base 10. The idea is the same in both octal and hex. So let me erase this. Taking the number 324, base 8, we're going to index it once again. So this is index 0, 1, and 2. Going from right to left, starting with this 4 here, we're going to multiply that by 8 to the power of 0, which is just 1. This will become 8 multiplied by 8 to the power of 1, which is 8. And this will be multiplied by 8 to the power of 2, which is 64. Now, I already plugged this into a calculator for you, and the final thing we get is 212 in base 10. You can check that on your own with your own calculator. Alright, so hexadecimal, again, when we're still going single digits, the idea is still the same. 873. Multiply this by 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. Again, we're going to index this from 0, 1 to 2. And plugging this into a calculator, you're going to get 2,163. But here we note that when numbers are greater than 9, they're represented by letters. So we have to be aware of this when we are solving for hexadecimal numbers with A and F. We have to replace that, or A through F really, we have to replace those with its proper decimal notation to make things easier for ourselves. So 10, 4, 15. The more problems you practice with, the more you'll be able to remember. It'll just come intuitively what A is, what B is, what C is, and you won't have to check this chart as much, but for now you can go back and refer to this, or even just write it out. Right, like to remind yourself, right, A is 10, B is 11. Okay, following the same process, we're going to get that this number, A4F here, is going to evaluate to 2,639. Okay, next, we're going to be doing some practice problems. So I encourage you to pause the video now, try all these problems out on your own, and then resume when you're finished, and I'll just go straight into the solution now. So remembering to index this, I'm going to write this out with a little bit bigger font so we can see. One, 0, 1, 0, 1, 0, 0, 1. All right, I'll space it out a little bit so it's a little bit easier to see. Okay. Remembering the first step is that we index this. So 0, 1, 2, 3, 4, 5, 6. I have to write a little bit small here. 7, 8, 9. Okay, so once we've indexed this, we can start multiplying it just using decimal. Now that we've already indexed, we don't really need to start from the right, as long as we remember that we need to multiply whatever digit this is by 2 to the power of its index, so 9. And then for binary, it's a little bit more straightforward. You could just see that there's a 1 here, then that means you add another 2 to the power there. For those of you who don't know, this caret symbol is the power sign. Okay, now I just have to plug this into a calculator to figure out what this is. So, luckily enough, I'm gonna switch to my calculator tab, put this in, and as you can see, it says that the result is 937. So that'll be our answer here. 937. For here, we do this once again. Let me see if I can make this font a little bit bigger. Seven, 2, 4, 1, 0. And we'll index this again. Write out its equivalent using 8 powers of 8. And then we'll plug this into our calculator. Ooh, it's getting a little bit messy. And we get 29,960. And I'm gonna copy and paste that back here and put it as our answer. Finally, we have our hexadecimal number. So we're first going to index it. Then we'll write out powers of 16. Oh, and remember here that we need to replace each of these with its corresponding number value. And remember, if you don't remember the chart yet, If A is 10, B is 11, then C is 12. It's always useful to think about that chart. Alright, and now our last answer, 718,892. And we're going to put that in here as our answer. Alright. So let's move on to our next topic here, which is converting from decimal. So we just learned how to convert to decimal, and now we want to learn how we can convert it from decimal. This is a little bit more tedious since it's not as easy as just multiplying the digits by a number, but rather we have to find how many times successive powers of the base can multiply into the number starting from the largest power. For example, if we had the number 300 here, we can pull up our calculator, but if we're gonna find how to write 300 in binary, first we have to see what's the largest power of 2 that can go into 300. For this, I might know off the top of my head that 256 is a power of 2, and it seems to be the largest power that goes into it. But what I didn't know off the top of my head was what power of 2 that was, but we have that written here. 256 is 2 to the power of 8. And then we'll take 300 and, well, we already have 256 here, and we want to add more to it to make 300. So I might start testing. I know the next lower power is 128, but that seems to go over 300. So maybe we'll try with the lower one. 64, that's still over. 32, that seems to be just fine. So 32 is the 2 to the power 5, which we will add here. Add a 1 to it here. And then we want to keep going because we're not at 300 yet. So maybe I'll add 16 next. That's just slightly over. So let's keep going down. 8 is just right. And finally, we add a 4 and we have exactly 300. So 8 is 2 to the power of 3 and 4 is 2 to the power of 2. Let's see that here, 2 to the power of 3, 2 to the power of 2. Now we're not just going to write 1, 1, 1, 1, because then that's going to scramble the order of the indexes. But if you remember earlier when we were converting from binary to decimal, we indexed the number. So here we kind of do the same thing. We're going to index this number, and we're going to put a 0 wherever, well, it doesn't show up in our sum here. And we're going to put a 1 wherever it does show up in our sum. Alright, so as you can see, we had a 1 at 2 to the power of 2, which you can see here. We had 1 at 2 to the power of 3. We have 1 at 2 to the power of 5, and 2 to the power of 8. And we're not going to have any leading zeros, because we don't have that in decimal either. So we're not going to have that in any other number system. And this is our final answer. Okay, so for octal, we have to do this process again. So 300, oh, except this time, let's see. I might know that 8 to the power of 2 is 64, but 64 is much less than 300 if we're gonna just keep adding powers of 8, that's right. 8, and then finally 1. You notice the maximum you can get is only 73, and that's nowhere close to 300. So instead of just going immediately down to the next power, with bases that aren't 2, you usually are able to add on the same power for as many times as is necessary. In this case, I'm going to keep adding on 64 until I go over 300. And here's where I go over. So I start going to the next power. So 8. So we're going to just keep adding our 8s. And look, we went over. So now let's start with 1, and then we just fill up the remaining with 1s. And then we count how many there are. So this was 4 times 64. This is 5 times 8. And this is 4 times 1. So we're going to go back here, and we write our answer. We're going to have 4 times 8 to the power of 2, 5 times 8 to the power of 1, 4 times 8 to the power of 0. And then if we just simply index, this is 0, 1, 2, so we write 4, 5, 4. In hexadecimal is the same idea. You're going to take 300, 256 is the largest power that goes into it. 300 subtracted by 256 is 44, and 16 is the next power of 16. And 16 can go into 44 2 times. 44 minus 32 is 12. And we only have the 1s left, so we remember that C corresponds to 12, and we write our final answer as 1, 2, C. Alright, let's do some practice problems. So convert 395 base 10 to binary. Alright, let's go to our trusty calculator again. So our goal is 395. Let's start testing with powers of 2. So let's see. Our goal is 395. Actually, I'll write that here so we don't forget. 2 to the power of 8 seems to be the largest power of 2 to go in, because the next one would be 512, and that's over. And so let's keep adding powers. Oh, that goes over, so let's try a different one. And we're going to just keep going down until it doesn't go over. Just slightly over. Alright, now we see that we have 1 at 8, 7, 3, 1, and 0. So when I write this in binary form, if you don't want to index it every single time, you could just start from right, write the number from right to left. So here you see you have a 1 at 0, you have a 1 at 1, you don't have anything at 2, at 3 you have 1, nothing at 4, 5, or 6, but 1 at 7, and 1 at 8. And that would be our answer. A little bit messy, but it might be a more convenient way to write this. Alright, let's see the next problem. So 1034 to octal. Again, okay, I'm going to write this here again. Again, our goal is to get a sum that reaches it. So I can see that 8 to the power of 3 seems to be big enough, but can I add another 8 to the power of 3? Maybe multiply this by 2. And I see, ooh, that's just under, so we're almost there. So maybe I can just eyeball it and see that 64 isn't going to fit in there, so I'm just going to go ahead with 8. Ooh, that's almost there, and it seems we'll just need a 2. So it's implied, but this is 8 to the power of 0, and this is 1 times 8 to the 1. And then again, when we write this, it seems that we can just go from right to left. Oh, hang on. It's not actually 0. This should be a 2, and at 1 we have a 1. There's nothing at 2, and there's a 2 at 3. So 2012 is our answer. Alright, same thing for our last one. 5,551 to hexadecimal. 5,000. Let me check that's the right number of 5s. Right, 3 5s. Okay, so let's try to experiment. Oh, 16 to the power of 3. That's a pretty big number. So maybe we'll try with 16 to the power of 2 now. It seems we can do a lot more multiplication here. So I'm just gonna start really testing the boundaries here with some random numbers. It seems 5 was just about right. So let's see how many more 16s we can fit in. Oh, that's almost there. Oh, as you can see, we're going into the 10s now. Here's where we're gonna have to... Oh, wow, okay. Right, that's 15. And then 15 times 16 to the power of 0. Here is where we went into the double digits in decimal. So we have to remember again when we write it, this is going to be converted into F, A, 5, 1. Oh, I noticed I made a mistake here. That should not be 0. This should be 1. So 15AF is our answer. Alright, finally, I think we have one more topic. Converting between binary, octal, and hexadecimal. This is actually one of the easier topics, I think, is at least maybe the easiest of these. So from octal to binary, all you have to do is replace each octal digit with corresponding 3 binary digits. So for example, if we split 375, then for each digit 3, we have to write that in binary, 0, 1, 1. Except we have to keep the leading 0 because it's not very noticeable in this example, but if you had a leading 0 here, you have to keep it because it's in the middle. It's technically in the middle of the number, like this one, really. Oh, wait, let's go back. Okay, so 3 in binary is 0, 1, 1. 7 in binary is 1, 1, 1. 5 in binary is 1, 0, 1. And then you just remove the spaces in between. And then here I got rid of the leading 0, so this is the number it's going to turn out into. Hexadecimal is almost the same, except you replace it with its corresponding 4 binary digits. You see, the reason for this 3 is that the largest digit, 7, only requires 3 binary digits, so you don't need 4. And the largest digit, F, is going to require 4 ones in binary, so it's going to need 4 digits. And as you can see, A is 1, 0, 1, 0. And then you're keeping all the zeros in between, just getting rid of the space here and rewriting the number like that. So when converting back from binary to octal, you just group binary bits in 3s and convert each group into octal. Okay, so here's where we have to be a little careful. We have to start grouping from the right side. So first this 0, 1, 1, as you can see here. And then this 1, 0, 1, as you can see here. And then you might notice that there's a leftover there. What do we do here? Because there's not enough digits. Well, we simply add in this leading 0, because remember, leading zeros can be ignored. So it's okay however many leading zeros we add. Either way, we'll just convert that into octal, convert each of these binary into octal, which is basically converting it into decimal. And then from binary to hexadecimal, you group in 4s, so starting from the right side. Here we have a 4, here we have a 4. This is perfectly in 2 groups of 4, so we didn't really have to do much. We just have to convert both of these separately into hexadecimal. Alright, let's try some practice problems. So let's convert 391 octal to binary. Okay, so let's first separate the digits a little. 3, 9, and 1. And we know 3 in binary is 0, 1, 1. 9 in binary is... Oh, okay. I'm so sorry, but this isn't even a valid problem. I was wondering, like, wait, 9's not a valid octal digit. Okay, that's a mistake I made when I was making the problem. Let's let's convert 371 to binary instead. So 371. So we know 3 is 0, 1, 1 in binary, 7 is 1, 1, 1, and 1 is 0, 0, 1. And then you just get rid of the spaces, rewrite it like condensed. Just be careful you don't miscount the ones. And I know it's like rather horrendous writing, but yeah, that's our answer. And convert this back into hexadecimal. We start grouping from the right side. And then for the leftover 2 digits, we're just gonna add in 2 zeros here. You can't see it very well, but those are 2 zeros. And then we can rewrite this. So this has 15, so which is F. This is 8 plus 1, 9. This is 8 plus 2 plus 1, which is 11, B. And this is 0, 0, 1, 0. This is just 2. So this is our hexadecimal number. And okay, here's a little bit of a tricky variation. So how you do this is first, well, actually, let me clear everything so I have more space. So I'm going to write this up here. 4, oh, I don't think that's going to be enough space. 4, 9, C, 2, E. Okay, so we know that 4, okay, first we have to convert, this is base 16, so let's convert that to binary. 4 becomes 0, 1, 0, 0. 9 becomes 1, 0, 0, 1. C, which if you recall is 12, becomes 1, oh wait, 1, 1, 0, 0. 2 becomes and E, which is 14, will become, and then since we're converting this to octal, okay, let me write this a little bit more condensed. All right, since we're converting this to octal, let's now convert this from binary to octal. So we're gonna group it in 3s. We're gonna give this group a leading 0. Oh, it already has another leading 0 here, so we're just adding another one. And then we can convert this to octal. So we can start left to right, whichever way, as long as we maintain the order of the groupings. This becomes 1, 1, 1. This is 5, 0, let's see, 4, 5. And that's our answer. Okay. So besides these kind of problems, we have a few other miscellaneous problems here. For example, if we're solving for this number in base 2, and we have to convert, and we have this assortment of other numbers in other bases, then we might have to convert these to a common base. For example, we could say we work best with decimal, so let's convert all of these numbers to decimal, and then convert that to binary. So remember, converting these to decimal, we have 3 times 8 to the power of 1 plus 1 times 8 to the power of 0. To save a little space, I'm going to start just writing this as 8 and like simply 1 to just, as I said, to save space. And this is 10 times 16. Oh, a little bit careful here. And I'm just gonna turn this into, I'm just gonna like solve this out the old algebraic way. And then we just have to convert this decimal number to binary. So I'm going to go back to my calculator. the number we're solving for here is 1645. So let's go wild and 2 to the power of 10. And use a couple big powers. Hang on, I don't quite remember what my number was before that. Ooh, it seems that I can go with some pretty high numbers here. Oh, let me see, 1600. So we probably need a power of 5 here, and we probably need a power of 3. And there we have it. If we just remember, use the indexing to rewrite this, this will be our answer. And then our next problem here is, what's the difference in the number of ones between the number with the most ones in its binary form and the number with the least ones in its binary form? So what this problem is trying to say is, let's convert each of these numbers to its binary form and count how many ones there are, and then find the difference between the least number of ones and the most number of ones. Okay, let's start from this into binary. So, alright, let's go back to calculator. Our number is 4 ones, and this is in decimal. Oh, it's not quite right. Sorry, I forgot to turn off my alarm from earlier. So let's just experiment here a little. And then since this number is only asking for the number of ones, counting the number of ones, not for its binary form, we don't really have to convert it. We just have to know how many ones there are. So in this case, we have 1, 2, 3, 4, 5, 6 powers of 2s that we've used, so that's 6 ones. Let's see, for the other numbers, 314, converting that to binary. Wait, actually, let's keep track. We had 6 ones here, so let's write that down. This was 6. Okay, so now here we have to convert this by, remember, rewriting each digit into its binary form. And here we count 1, 2, 3, 4, 4 ones. This is less than 6, so it's definitely not going to be the max, but it could be the minimum. Now let's see the others. 1, 2, 3, 4, 5, 6, 6 again, so still our max. Okay, now we have, this is in binary, by the way. That's why I'm just counting. This is in hexadecimal, so we have to convert all of these A's into its binary form. But if we notice, since they're all A's, and we know that there's only 2 ones in the binary representation of A, we just multiply 2 by 4 times, so we know pretty easily that this is 8. So that seems to be our new max number here. Okay, and then we have another decimal number we have to convert. So 7, 7, 7, 8. In this case, we might actually need like larger powers of 2. Okay. Let's delete all of these since we have to prioritize larger powers. And there we have it. This is 1, 2, 3, 4, 5, 6, 7 ones. So it's neither the max number of ones nor the minimum. So it's just there. And here we have our minimum 4, our maximum 8. We'll take the difference, and our answer will be 4. Alright, that's all for this topic today. I hope you guys enjoyed this video, and please remember to leave a comment and like about what you thought about this video. Whether it was helpful, if anything new you've learned. Okay, see you next time.